So I think we'll get started, and we're on notes at 6.2. I just want to recap a couple of things. We'll talk a little bit more about sintering, and then we're going to start on a different topic, namely polyjet, which is a hybrid between photopolymerization and making 3D printed parts with inks. And so we'll have a lot of interesting things to talk about there, and that serves as a transition between powder-based thermal processing and photopolymerization for stereolithography. So before I get started on the slides, any questions? All right, so I just wanted to remind you that there are some papers out there on ideally what polymer powder should look like. But with experimental powders like this one in a composite powder, there's a lot of different things going on. So you see the elongated fibrous character of some of these particles. You see some holes. You see some places that are sintered and not sintered. And so this is a hard part about inventing new material feedstocks or dealing with composites in sintering processes like high-speed sintering, or multi-jet fusion, or SLS, which we've been talking about, is the polymers or the powders of the different feedstocks play a major role in what the final parts look like. So the morphology of the powder is key, and we're still learning about the best ways to make powders and the best ways to study those powders to get them performing in these processes. So that's just a reminder on 6.2. We're actually going to go back to notes at 6.1, which you can find in Box. And so I'm just going to bring that up. And so we've been talking about SLS for a few lectures, and we covered HP multi-jet fusion last time, and we're going to talk about that a little bit more today. But multi-jet fusion is really an offshoot of high-speed sintering. And so these are still powder bed fusion type of processes because it's powder bed, but it's a little bit of a hybrid process between binder jetting, although the inks are not really binders, and sintering. And so high-speed sintering has been studied for a long time. As a matter of fact, it was invented at Loughborough University by Neil Hopkinson. And so they have a bunch of different papers on the physics of high-speed sintering, how high-speed sintering is used in comparison to SLS, and sort of the nitty-gritty of how the process is optimized. Now, the original high-speed sintering work at Loughborough was always done using black ink. And so that's reasonable because, of course, things that are black tend to absorb a lot of IR light. And so you can get very concentrated heating where the ink is. Tim Ayers from class brought up a really interesting point. Well, how do you high-speed sinter clear materials or white materials? And HP discusses that. We'll talk about that as you go to multicolored inks. But there's a lot of good information on HSS if you want to look it up, and a little digging on Google Scholar or your favorite scientific paper database of choice will help you find the detailed information if you want to dig in further. And we're going to discuss a couple of key papers coming up in this lecture. So this is just from one example from the Loughborough group. And so they're looking at different laser powers. So 1.18 kilowatts, 1.7 kilowatts, and 2 kilowatts. Now this is just the lamp power setting. And so there's some questions on what the energy density is, or what the fusion temperature is. Those things are hard to determine without some detailed measurements, but this is a nice engineering study. Once you've built an instrument that looks like this as you're trying to optimize parameters. You can see now what the different surface texture looks like at the couple hundred micron scale. So these are optical microscopy of these different surfaces. So they're trying to get good sintering, but of course, the less or the lower laser or the lower infrared power you have, perhaps you have better recycling, perhaps you can move the lamp faster, the lamp lasts longer, and so you want to find the sweet spot there where you're getting good sintering, but not over sintering of this material. And this paper that's referenced right here shows a nice comparison between a traditional SLS process and the high-speed sintering process. And this is actually the HP multi-jet fusion, but in most cases, especially in Europe, where high-speed sintering is pretty popular, the multi-jet fusion is just an offshoot of high-speed sintering. And of course, high-speed sintering is not necessarily on the ASTM diagram. Let me see if I have an ASTM diagram here. No, I don't have it here, but it's still a powder bed process that you're fusing. So it would fall under powder bed fusion in the ASTM, although it's a little bit of a hybrid because of the inking. But anyway, this gives an idea of what the surface roughness is for these two different processes, percent crystallinity in your polyamide 12 polymer, and you see the moduli are sort of on par. Tensile strengths are on par, but of course the elongation to break is pretty low for these powder-based processes. So because they both use powder, that leads to low elongation to break. And so we see that again and again that these powder-based processes, even compression molding data, which we looked at last lecture, shows low elongation to break. Compression molding is done with powder as well, although it's not a high-speed process. And this paper from the previous slide that's referenced again right here shows all the different types of powders along with things like build rate, different materials, different properties, etc., of the printing processes that tend to use powder-based feedstock. And so you can take a look at these. Of course, if you want custom powders, those can be made, and we've talked about how to make powder, but there isn't as many feedstocks for powder-based polymer additive processes as there are for like material extrusion AM or something like that. So this is a drawback of using powder in addition to the low elongation to break. So any questions so far, any things that people want to bring up? All right. Now let's switch over to lecture 6.3. So you can look in the menu here on box. So this is lecture 6.3, and I just titled this Sintering 2 because there's a couple things that I wanted to finish up. And then this is the last set of slides that we'll have for thermal sintering of polymer powder. So after today, if we haven't covered something that you want in terms of thermal processing of polymer powders, shoot me an email. We can discuss it over office hours, and we can talk about applications that you're interested in or something else. So like I said, there's a lot of ways to make polymer powders, and there's a lot of literature out there on how to grind polymers. So this is a grinding process, and how to get different particle sizes as a function of processing time. And so no matter what temperature you're at least for this polymer, so this is polystyrene, which of course is a glassy polymer. But anyway, no matter what temperature you're at, you can get a pretty good reduction in particle size on the order of an hour or 2 hours, or let's say 3 hours, because this is going to be 200 minutes, which is a little bit over 3 hours and further. But this takes time to process powders. And what that does is it adds cost to polymer feedstock. And since this is a materials focused class, we won't go into the detailed economics too much of 3D printing or 3D printing feedstocks. But for instance, polystyrene raw material might cost something like $1 a pound. Or let's take something easy like ABS might be a couple dollars a pound. When you buy a pound or a half kilogram of ABS filament, it can cost you $20 or $30. And then if you want to buy powder, the powders might cost $100 a pound or $70 a pound. And so every time that you try and get polymer feedstock in a customized form, it's going to cost money due to compounding, due to processing, things like that. And so that's why the injection molding industry is really settled on these polymer pellets, and the polymer industry is good at making pellets, but anything other than pellets, powders, filament, etc., is going to cost more. And so the 3D printing industry is struggling with that. Polymers, yes, are inexpensive, but some of these feedstocks cost significantly more because of the processing time. But there's a lot of different ways that you can process powders. Of course, you can get these different morphologies. And so from this reference right here, this is just more looking at the different morphologies of these polymer powders. And we've seen studies like this before, but this gives you a range of, or an idea of the range of types of particles that people are looking at for all of these powder-based processes. Also, this is a nice paper right here about multi-jet fusion. So this is multi-jet fusion, or HP, multi-jet fusion. And we haven't looked at print orientation effects too much, but there's a lot of print orientation effects studies out there where they print tensile bars in different orientations. So they have the pull axis of the tensile bar, in this case in the Z orientation, or they have the pull axis is in the X orientation, but this is oriented up on its side, versus the same orientation in the pull axis, but this is oriented across. And so what this study is showing between the dotted lines, or sorry, and the bright lines, the legend isn't on here, sorry, but for the solid lines, this is comparing multi-jet fusion versus orientation. And this is showing that there aren't lots of different orientation effects. So you see the span of properties as the part is oriented. It looks like the maximum strengths are going from about 45 megapascals up to 55 or so megapascals for all these different orientations. And so we can conclude that there's not large orientation defects in multi-jet fusion. And that's usually because there's good interlayer adhesion. And so we saw before for material extrusion AM, there can be big anisotropy in the part because it's really hard to adhere the layers to one another and get good interlayer adhesion in material extrusion AM. But for sintering, we tend to get good melting of one layer into the other. And so we see some spread of the data here but that could just be statistical error as well, or experimental error. And so this is not big orientation effects. And so that's a plus for multi-jet fusion type of processes. And this is just showing, again, the different strengths compared to some standards. So this Russian GOST normative, this is just a standard technique. You can read the paper. So instead of an ASTM standard, other countries and other areas of commerce have different standards. And so this is just a standard technique for mechanical property testing. But you see this elongation to break is relatively low. So that's an issue. If we look back here, the strain to breaks are not high. And so again, when you're using a powder-based process, this is the issue, is you don't get a lot of elongation, and so this really affects the toughness, as we've discussed before. Whereas the control samples have, these are the two, oh, let me erase this little part right there. So these are the printed samples, these are the controls. They have better elongation to break. And that's something that the industry is struggling with. How do you get good sintering yet process from powder and get good elongation to break to get tough parts, parts that can withstand impact, parts that can withstand some flexing and don't have high strength but are brittle and just break after low elongation. Any questions so far? All right, so this is a nice paper right here. Here's the reference. And this is just comparing SLS versus multi-jet fusion. And this is a nice recent paper from 2019. So there's a lot of good information in there, especially if you're interested in the details of how these processes work and comparison of parts. And so I just put this diagram up here because traditionally in SLS, the powder is spread with a roller. And of course, you have a point source. Oh, let me get point in there. That's scan versus having your inkjet printhead and an IR lamp that gives full illumination in multi-jet fusion or high-speed sintering. And then they discuss a little bit about spreading powder with a blade versus spreading powder with a roller. That's just a technical issue, and you can read more about that if you'd like to. But anyway, these are nice diagrams comparing the two. What's really interesting in this paper is that they talk about the powder morphology. So this is HP 3D printed nylon powder, which is B right here. So this is HP. And this is DF nylon. And this is by 3D Systems, which is going to be SLS. And so what they did in this paper was that they were looking at new and recycled for each of the DF or the SLS powder versus HP powder. And of course, this is branded powder from these two companies. They didn't say who made the powder or who made the polymer in the first place, because of course 3D Systems and HP don't make polymers. But anyway, they were looking at the morphology and then looking at the molecular weight in terms of recycling powder versus new powder. So the molecular weight is a little bit different for the powders, and we can just look at the MNs. And if you're interested in polymer science, we can talk about the dispersity. But if we just focus on the number average molecular weights, we see that the SLS powder from 3D Systems is a little bit lower molecular weight, but when it's recycled, you get significantly higher molecular weight. And so after you put the powder through the process a couple times, and the recycled powder, remember, is the unfused powder in the powder bed that's just been sitting at the bed temperature. Same thing with the HP powder. The HP powder was even illuminated. It just wasn't fused with ink. But you can see that the recycled powder doesn't have a big increase in molecular weight. And so they talk about the polymer chemistry in regards to this. The HP powder is end-capped, which means it has chemistry on the end of each chain, which facilitates the molecular weight not increasing when the material's heated up. So we can think about eggs, which are proteins, which are polymers, right? And you cook eggs or you vulcanize rubber, and the molecular weight goes up. So when you heat polymers to some sort of high temperature, they can degrade, and one of the modes of polymer degradation is the molecular weight increases due to cross-linking. But if you have the right chemistry in your feedstock, so not only whatever particle size and particle size distribution you want, but the right end capping or the right additives, you can prevent this molecular weight increase as a function of aging or recycling, and that can influence the performance of your parts. So this is one of the only studies that I was able to find for fusion processes that looks at molecular weight and polymer chemistry in regards to the performance of the powder, at least in terms of recycling. So that's cool. I suggest taking a look at this paper to get the details on that, but I wanted to bring it to your attention. And what they did furthermore in this study was that they compared, again, the DF for whatever reason is SLS. It's the Duraform feedstock from 3D Systems that they use in SLS. So they're just using a shorthand of the trade name. But anyway, you see that the stress strain curves are pretty similar for the two processes, at least up to a certain strain to break. And so for the HP process, at least in this study, they're getting a little bit higher elongation to break for the HP process in compared to the SLS. Now, these types of studies really depend. How good are they at SLS? Are they using the latest techniques? Are they trying to focus on HP processes? Is this really a group that's experienced in high-speed sintering? And so you oftentimes have to look at this type of data with a skeptical eye, because the question you might ask yourself is, are they using the best SLS conditions? But based on everything else that we've seen, elongations to break or strains to break of 5% aren't unreasonable for SLS. It's just that they're getting pretty good performance from their HP process in regards to elongation to break. And so that's just an interesting observation. They also show surface roughness. So this is a surface roughness map. And so they're showing the heights. So you could think of this as a topography or the hills and valleys of the sample according to this scale. And they say that the SLS is a lot rougher because it's got a bigger difference between the highs and lows as compared to the multi-jet fusion HP process. And so we've talked about surface roughness before. this is just a nice demonstration where they're looking at the different properties of these parts and comparing the two processes if you're interested in what process might be better for whatever application you're interested in. So, and again, this is pretty recent, 2019, so I urge you to check out this reference if you really want to take a deep dive. There's a bunch of other properties that they compare in there if you want to take a deep dive on these sintering processes. So I'll pause here and just ask if there are any questions from the class, anything that people want to talk about. All right. So we're going to finish up with a couple questions that Tim Ayers and I were talking about over email. And so this was a good heads up. And we had, or Tim had some questions on how does HP fuse using IR, how do they fuse non-black inks? Because we know that in HHS, your fusing agent is usually black. Oh, sorry. Is usually black because it absorbs IR. But because we're going to come along and this is an IR fusing lamp. But in the HP process, they have all sorts of different colors. So how do you get this multicolored object, or how do you get white parts out or clear parts out of HP multi-jet fusion? And so all you need is IR is usually between 4 micron to 20 micron wavelength light. It turns out that there's lots of things that absorb in that region, and some of them are white, some of them you can make clear, and it's just they're a little bit more expensive than carbon black or some of the other black pigments that are used in high-speed sintering. So how do we sinter things that are not black or dark like high-speed sintering? And the key is found in some of the HP literature, and we'll cover that in a second, but they show this diagram. And so this diagram from HP comes from this technical note from Saratech right here. But this diagram is a anatomical model. And it looks like an anatomical model of lungs or something like that, or heart, or you know, something that surgeons use to think about what you know, how to plan surgeries, or for education. You know, we've all seen the sort of skeleton in the corner at the doctor's office. That's used to illustrate what's going on in medicine. And it turns out that there's big money in making these custom anatomical models for surgery planning, for education, for making prosthetics, other things like that. And so HP is trying to get into this market where usually polyjet processes are used to make these anatomical models. And we'll go over anatomical models when we move to polyjet in a sec. But the one thing you can see is that you have some surface roughness in HP multi-jet fusion because it's powder-based. And soon we're going to compare to polyjet, or droplet jetting or drop-on-demand technology that doesn't necessarily have that surface roughness because it's not powder-based. So this is a really interesting sort of detail if you want to compare different techniques or compare different printers that are good for different markets. But anyway, HP wants to get into this making anatomical model space because, of course, hospitals pay big bucks for this. And so what HP says is that they had to find bright fusing agents. And so they call this HP Bright. They don't tell us what it is. They said after an exhaustive search and they scoured the world, et cetera, which is just marketing talk. But they needed a fusing agent to fuse cyan, magenta, yellow, and black. So of course, these are all of the colors in inkjet. So if you buy a inkjet desktop printer, usually there's cyan, magenta, and yellow cartridges, and then the black cartridge. And so this is a full color printer, and they just put these fusing agents in order to get this 3D sintering. So this is really interesting because HP, of course, has made inkjet printers for a very long time, and they figured out how to adapt that same sort of technology for 3D printing. And so this bright fusing agent, they don't tell us what it is, but this may be a metal oxide. It may be an organic molecule. Who knows what it is, if anyone figures out what these bright fusing agents are, but this absorbs 4 micron to 20 micron IR light to heat up. Turns out lots of things heat up when exposed to that wavelength in order to melt the powder in the powder bed for the multi-jet fusion. So this is cool. Tim found this paper, and so with just a little digging and a couple emails back and forth, we were able to fill in the gaps of how HP was doing this fusion with different color inks. And they disclosed that they're using a different fusing agent. We just have to look in the patent literature to see what fusing agents are out there, what fusing agents has HP patented. So fusing agent chemistry is probably in patent literature. And if you've ever looked at HP's patents or HP's patents in 3D printing, there's hundreds of them. And so this will take some digging to figure out the possible range of fusing agents. So if people are interested in that, we can discuss it further, but we won't talk a lot about patents in this class. Any questions so far? All right, Ceratec also has a really nice case study on the cost of using multi-jet fusion technology for insoles. So these are for shoes, of course. And these are the inserts inside shoes that like orthotics that people wear, or like cushioned insoles that folks wear so they can adjust the fit of whatever shoes you're interested in. But they have a really nice case study on the economics of using multi-jet fusion technology to produce these insoles. And so they say that you can get, at least 7,000 pairs per year of these. And so that's a good number, up to 20,000 pairs, because eventually you're not going to be able to produce as many insoles as you want. So for more than 20,000 units per year, you might have to go to conventional manufacturing. Or another 3D printing technology. So this is interesting because this is giving us some numbers now on what size part count per year we might expect from a 3D printing operation. So this is just done for insoles, but we're looking really at tens of thousands of parts or even thousands of parts for manufacturing using 3D printing technology to make sense. And we'll talk more about this later when we talk about different markets and we touch on different industries that polymers and composites are used in for additive. But this is a really nice case study because it gives numbers of what's going on. Any questions? All right. So just like there's papers on multi-jet fusion parts, there's some really nice papers on high-speed sintering. Which of course they're related to one another, and this is one of the papers right here. So you can just type that DOI link into your web browser and pull out the paper. But here they're comparing now Duraform polyamide. So this is the polyamide powder, and they're looking at ultimate tensile strength, comparing SLS versus HSS. And so the elongation to break, the ultimate tensile strength, and the Young's modulus are all very good and comparable for this polyamide, which is a glassy semicrystalline polymer. They also had this nice comparison comparing this TPE. So TPE stands for thermoplastic elastomer. And you can tell it's an elastomer because the elongation to break is relatively higher. So for the glassy semicrystalline polyamide, which of course is a type of nylon, and we know that nylon is a hard polymer. You see the elongation to break got up. And here's the elongation to break right here. We're on the order of 10 to 20% elongation to break, where for elastomers, we're on the order of 100 to 300 or 350% elongation to break. So this is elastomeric flexible behavior. The Young's modulus is lower. The Young's modulus is on par between the two. But with high-speed sintering, what they're claiming in this paper is that they're getting really good elongation to break because they're getting very good fusion of the powder because they can put the ink in there and they can really dial in the fusing conditions for this elastomer. Now, again, we have to question whether they're using the best conditions for SLS because this isn't an SLS group. And so what machine are they using? Do they have the best material for SLS, et cetera, et cetera? But this is a nice result, at least for high-speed sintering, showing you can get very flexible parts that have similar strengths to what's available in SLS. And the one tweak that you can do in high-speed sintering or multi-jet fusion that's not as easy to do in SLS is this right here, or the grayscale of the ink. So the fusing agent can be applied at various densities. And so that's what grayscale is, or that's also called dithering. So you have these different dither patterns. So the grayscale is here. And so that is an undithered pattern where it's just different lightness and darkness based on the pixel density that this is displaying at, where dithering is white and black at different densities. And this is sometimes called halftoning, because you can make your eye see different shades of gray depending on the dot density that you use. And so this is now really interesting, because if we have all of these inkjet heads, or we're dealing with droplets of ink, how many drops per millimeter we use will give us this effect. And then the fusion that we get will depend on how much ink is deposited within a certain area. And of course, we can, in SLS, you can vary the laser power, you can vary the scan speed. We talked about the energy density of the fusing laser. And so you can get some of this same effect in SLS, but with high-speed sintering, you can control this directly by how many dots per millimeter of fusing. I'm running out of room here. How many dots per millimeter of fusing agent you use. So that's interesting, and this allows people doing HP multi-jet fusion or high-speed sintering to really dial in the sintering conditions, and gives a little bit of a different handle than you have with SLS. And so in this nice paper right here, and this is from Neil Hopkinson's group, who was inventor of HSS, they're looking at the percent crystallinity as a function of grayscale. And so you see a slight variation in the percent crystallinity depending on how much fusing agent you put down, depending on the grayscale. And this is dots per millimeter right here. So they're showing, in effect, how much, degree of particle melting you're getting based on how much toner you're putting on there. So the one real issue that you have is that even though the crystallinity changes a little bit, you see that the mechanical properties can change a lot. Now, for high crystallinity samples, what they've shown is that in general, you have lower Young's modulus. So this is too much crystallinity because you have a lower degree of particle melting versus something has less crystallinity. Now, this is different than for melt processed polymers, because usually in melt processed polymers, we have modulus versus percent crystallinity is linearly related. And we saw that way back in the very first lecture, second lecture, when we talked about polyolefins. And so what's happening is this degree of particle melting, or this right here, and this is just some parameter that they came up with to describe, this describes fusion of particles in powder bed. So you need to have good fusion or an increasing degree of particle melting in order to get the properties you want. And same with elongation at break. So if you have poor fusion, even though you have high percent crystallinity, remember these are for melt samples. And if they're melt samples, like in injection molding or something else, these are fully fused. Whereas if we're processing out of particles, we need to be able to balance the degree of particle melting with the percent crystallinity. And it just so happens in this process that it's hard to get really good melting if you have crystallinity that's too high. And so all of these parameters need to go into figuring out, how do we get good fusion? How do we get strong parts? And some of the relationships that we develop in these sort of high-speed sintering powder-based processes are not the same sort of thing that we would encounter from melt extrusion. So this is an ongoing story, and this is how people are learning how to build engineering parts using these fusion processes that don't obey some of the same rules as melt process polymers. So again, the story is still evolving here, but these are some things that you should be aware of if you start to produce parts out of additive manufacturing. Any questions on this? Any comments, things that people want to bring up? So this is the last slide on powder bed fusion type processes. We're going to talk a little bit about binder jetting, but we're not going to talk as much about the powder fusion part of it, because there really isn't much powder fusion in binder jetting at all. It's more about how polymers stick powder together. But is there any questions, any comments on fusion of polymer powders or thermal fusion of polymer powders? All right. So I'll take that as people are interested in this. And of course, there's a lot of things going on, but there's not as much hands-on research that's done with powder bed fusion processes. They're just harder instruments to get a hold of, although there's a lot of HP instruments coming online. And so I think there'll be more and more information out there as we go further. So we're going to switch gears here in the last 25 minutes of class, and we're going to talk about a new process in terms of making polymer parts with drops of polymer. And so this might be called drop on demand. This is formally called polyjet. ASTM is going to call it material jetting. Sometimes you see it called Connex. That's just the name of a printer, or objet. And we'll talk about how this process is used, and we'll compare this to the powder bed fusion processes that we just discussed. So the way this starts, of course, is to look at the ASTM diagram, and we've spent all of class so far on thermal bonding from filaments, from melted materials, from powdered materials. And so what we're using is now chemical reaction bonding. We're going to have liquid feedstocks that are fed out of a printhead. So if we follow this down, this is called material jetting. And so that's very interesting. Before, well, what we just talked about was in high-speed sintering, this train right here. However, we really don't have chemical reaction bonding with the liquid. So it's not a perfect analogy for high-speed sintering, because in high-speed sintering, there's not necessarily, or there doesn't have to be a chemical reaction in high-speed sintering. It's all thermal. But now we're going to talk about there has to be a chemical reaction. There's a liquid polymer feedstock. This is also called a resin as well, and we'll talk about that. And then what we're going to do is the basic process, let me erase this arrow right here, of liquid reactive photopolymer curing. So this is familiar to you because, of course, a lot of you out there have used super glue. Some of you out there have had fillings where they have that blue light that they put in your mouth. That blue light is a UV light that they use to cure the acrylate photopolymer in your porcelain filling. If you've ever used two-part epoxy, that's not a photopolymer because you don't cure it under light, but there's some high-end adhesives that you might use in the lab that are UV cured. And so we're going to talk in detail about what photopolymers are and about what the reactions are to give this photopolymer curing in the SLA chapter when we talk about SLA. But for now, we're going to talk just about material jetting and how to build up parts with material jetting. And the reason that material jetting is put here is that before, this is material extrusion. You all know that. This is powder bed fusion. So this is material extrusion. This is powder bed. Including multi-jet fusion and high-speed sintering. But now we're going to use polymer droplets to build up parts. And so as opposed to something like HP jet fusion, where the structure or the structural, let me write that, not completely over. Is in the powder bed, right? We talked a lot about PA11, PA12, TPE. You know, what powder were we going to use to build the part? In polyjet, or if we go back, I'm going to call it polyjet a lot because that's the sort of colloquial name, but if I can get back here. In our material jetting, the entire part is composed of photopolymer. So that's interesting Now you build up an entire three-dimensional part using photopolymer inks. And so when we talk about material jetting or polymer droplets, the droplets are photopolymer liquid ink. And so you see a lot of interesting diagrams. We're going to look at a YouTube video in a second here. But now this is a fundamentally different process where we can put droplets of material where we want in 3 dimensions. And so this is meant to symbolize a printing head. And this is basically a 3D part built out of ink. And that's cool. And it's built out of a special ink that's fused together. But you can get good mechanical properties from these photopolymers if your process is done the right way. So polyjet, objet, conics, material jetting. What's special about this is that you have your print head. And so this is, let's say, your structural material. You're going to need supports for this too, because you're going to be able to do overhangs and other stuff like this. So these are, again, photopolymer liquid inks, not unlike the inks that are in an inkjet printer. However, there's some more polymer in there, but there's not as much solvent in there, things like that, because of course the inks have to dry and other things like that. What's in a photopolymer ink is it's all polymer. So they can be viscous. You need special print heads. You need some special pumps to be able to move these inks around, but they can be photopolymerized using this UV lamp. So these are basically liquid polymers with no solvent that are UV photopolymerizable. So not everyone in this class is super up on their polymer chemistry, but we're going to talk a little bit about polymer chemistry. Thermal shaping of polymers is easy to understand. You heat something up, it gets softer, you shape it. And so I think that a lot of people are comfortable with the thermal bonding part of polymer processing, but we do need to talk a little bit about the photopolymerization and the mechanism and some of the tools that are used to understand what parts can be built and how to build polymer and composite parts using photopolymers. So there's a lot of different photopolymers out there, and so we're going to hone in on some of the key chemistry, and that's upcoming, but I just want to set the stage here. And so what happens is this is layer by layer. The part is built up, it's rolled, and then it's fused in order to get your solid layers. So layer by layer, solid parts are built up, built in 3 dimensions. So has anyone ever seen one of these objet or Connex printers? We have a couple at Penn State. If you've ever seen it, you know, eventually someday you can look at some parts that are built with this technique. But this is something, there's a lot of good YouTube videos out there. We're going to look at one in a second. There's a lot of really interesting papers on this. People use these printers all the time to design prototypes. and do other things. And so I encourage you to look around out there and think about this specific process and how it might compare to the other processes that we've discussed so far. So this is just a different schematic. And what's cool about this paper is it's used in medicine and radiology. So this is used for anatomical models. And you'll see that the parts look really, really good because, of course, we can jet very small droplets and we don't need a powder support, or we don't have these lines in the part from roads. So you get very high resolution and you can get some reasonable printing speeds with this technique. So we're going to watch this video, if I can get it going, and this will give us a quick introduction to PolyJet or to material jetting AM. Okay, let's see how this goes.
PolyJet is a 3D printing method that makes beautiful, precise models in a huge variety of materials and colors. It works like an inkjet printer, but instead of jetting drops of ink, PolyJet 3D printers jet tiny droplets of liquid plastic. A UV light instantly cures the plastic, solidifying it. And so, layer by layer, complex models take shape. The most advanced PolyJet systems can build multi-material parts, soft, rigid, clear, and colorful. You can even adjust material properties like heat resistance and durability. The same technology that makes gorgeous prototypes also makes precise manufacturing tools. Designers can predict future needs and serve them now. Manufacturers deliver better products faster and with less waste. Researchers have new methods of saving lives. PolyJet is reshaping industries like film, fashion, and medicine. It's helping people with great ideas improve the future. What's next?
Okay, let's see if my slides come back here after that. But PolyJet is really interesting because you can make these really detailed models all out of polymer. And so you see the essential part in this slide right here is that you see the fusing lamp, or let's call it photopolymerization. Light. You see the print head. And because this inkjet printer has, you can integrate many different inks, you can get multi-material structures integrated in one part. So just like you can get multicolor printing in your desktop printer, you can get multi-material printing integrated into one structure. So of course, this is a toothbrush. This is going to be hard polymer. And this is going to be softer elastomer, and this is all printed together at high resolution because you're using these small drops. Any questions so far? Anything people want to bring up? Has anyone, I guess I was going to ask this question, I got going on something else. Has anyone seen one of these printers or seen parts from one of these printers? You can give me a thumbs up or raise your hand or something on the online.
I've seen parts printed by them. It was pretty impressive.
Yeah, sometimes they've shown different durometers in one sample, so you can get like from durometer 30, which is a relatively soft rubber, up to durometer 90, which is a relatively inflexible material. And so I agree, Eric, there's some really awesome parts that can be made like these. And it's just a matter of what are the properties. And so you see a lot of prototypes and a lot of models made using this printing technology. But because of the ink jetting nature and because the expense of the materials used, there aren't lots of products out in the marketplace that are made using material jetting, except for these anatomical models. If you want to call these products, you know, they're selling a lot of this capability to hospitals and doctors' offices. But when they're, you know, making an athletic shoe or making a helmet or something like that, these are just usually prototypes and not functional components that they would sell. But I'm interested in case studies where they've started to sell these parts out there and develop markets for this. Okay, so that's great, and other people can comment as they want. I'm looking at the chat, but these parts are worth taking a look at, and you know, someday I'll pass some around, or someday we can go back into the lab and you can take a look at these things. But we have a couple of these printers on campus, and you can also order these types of parts from some of the online depot suppliers. The question is, you know, a lot of these samples look like it's just material A and material B printed together. And so you can't have a bunch of different inks. I mean, maybe you can have 3 different inks or 4 different inks in this printer, but you can't have 60 different inks. And so one of the ways that they use to get different materials is that they use dithering, or they use this half-toning in order to mix different components of hard and soft. And of course, it's really hard to draw, or it's difficult, let's say. It's difficult to draw hard material and soft material, but in this case, we can use colors or we can use grayscale to represent different properties of polymers. And so let's say that black equals stiff material, and white equals flexible material. And we'll talk about the polymer chemistry that we use to get flexible polymers that are liquid versus stiff polymers that are liquid. But let's say in some examples, we would like a part or a component with variation in mechanical properties from hard to soft. What we might have to do in the old way of manufacturing is that we would glue hard component to soft component. You know, and that's not very sophisticated. We know how to do that, and we might want to do that if that's how we want to build the part. But with this idea of dithering, you know, we can't really make grayscale. This is hard to do with droplets because grayscale is really mixing of colors within a pixel. So you take a pixel that's 90% black and 10% white, and you get a gray, or you take a pixel that's 50% black and 50% white, and you get a different tone, or you get a different grayscale from 0 to 256, or from 0 to 255, or whatever you want, different grayscale levels. But if you only have drops, and you only have white drops and black drops, you have to do this dithering. So dithering is really based on density of drops in a certain area. And we'll talk more about this as we go on a little bit further, but you can think about the difference in grayscale or gray level, where within a pixel, you have a certain percentage of black versus a certain percentage of white. We call that the gray level, versus in that same area, you have a dithered sample where you have a different dot density of one material versus the other. And it turns out, depending on your perspective, or depending on your control area, they can give you very similar results. And this is hard to do with PolyJet, or impossible to do because it's difficult. Oh. To mix within a pixel. Of course, a voxel is a three-dimensional pixel, and we'll talk about that, but you should be familiar with pixels and voxels. Versus, it's easy to deposit voxels of different composition right next to one another in the case of dithering. And so dithering is how PolyJet works in order to get a full range of properties for whatever model they're interested in. And so there's lots of different types of dithering. And if you're interested in algorithms and mathematics, there's a lot of routines for dithering. So how do you take something that you might design so this is what you want, and you need to what can be printed. This is what the printing technology is capable of. And there's a lot of work right now trying to figure out the best algorithms to turn what your designs might specify into something that can be processed based on the available technology. So that's a lot to think about in terms of new process, some new materials, and new ways to make or mix these pseudo materials. So I think we'll stop here so people can absorb material jetting a little bit. You can check out YouTube as you're doing your homework and watch some of these material jetting videos. And this will start to get us into what photopolymers are all about and how we're going to use this chemical reaction bonding in order to make three-dimensional parts. So does anyone have anything they want to comment on, or any questions before we end class?
I don't really have a question. It's more of a comment. I received an email from Tim Simpson yesterday that Joe DeSimone, who is the CEO of Carbon, is going to be having a talk on Zoom on Thursday. It might be beneficial for some of us to tune in and hear what he has to say.
That's right. So Joe is the former CEO of Carbon. He he just moved to Stanford University. And what's interesting is the former CEO of DuPont is now running Carbon. But I will circulate that link to Joe DeSimone's talk. So he's going to talk about SLA and materials and photopolymers. But Joe is a real pioneer in terms of using science to do really interesting market stuff. So thanks for mentioning that, Eric. I will circulate that link, and I would encourage everyone to attend. Great. Anything else that people want to chat about? Okay, thank you very much. I will see you on Zoom on Thursday. Thank you.
Thank you.
Bye-bye.